Hey guys, in this video we're going to be discussing conductive heat transfer, and specifically we're going to be looking into Fourier's law, and our goal here is to be able to describe how heat transfers between media through a physical contact, in a medium. And the difference between conductive heat transfer and convective heat transfer is that in convective heat transfer we're dealing with moving fluids that are transferring heat away from something, but in conductive heat transfer we're dealing with direct contact. So that's what I want you to remember when you think of conduction. You think direct contact of two materials. And the first step in understanding heat transfer, and specifically conductive heat transfer, is remembering the definition of flux. And we can have mass flux when we think about dissolving oxygen into water, for instance. We can have flux of electrons when we're thinking about Ohm's law and V equals IR. We can have heat flux and when we're describing how amount or joules of energy are transferred between objects per area per time. And when I get confused about this stuff, I find falling back onto Ohm's law, which we remember as V equals IR, is very helpful for me, because when we look at this, and if we were to consider a square centimeter of wire, for instance, we can see the analogy between electricity and heat transfer. And so in the case of electricity, I'm going to draw this analogy. We can say that flux would be equivalent to current per an area, and this is going to be equal to some constant, which in this case would be 1 over R, our resistance, times voltage, because voltage is describing a driving force for an electron. So if we have a high voltage, there's going to be a high potential difference. An electron is really going to want to move from point A to point B within a copper wire, for instance, if you have a voltage. And so this flux that we see with electricity also will apply to heat and mass. But in the case of heat, because we're interested right now in conductive heat transfer, we will look at that. And then a final note I'd like to make when we're looking at this electricity analogy is that looking at this term 1 over R, 1 over resistance, this is equal to the conductance or the conductivity of your material. So if you have a really low resistance, your material is going to be really conductive, and vice versa. If your material is very if it has a lot of resistance, it's not going to conduct electricity that well. So you wouldn't expect to get that many electrons through it if it's really pushing against you. And so this same intuition is going to apply when we start to look at heat. And so getting into it now, if you look up the Wikipedia definition of Fourier's law, what you're going to find is this. It's going to tell you that Q with a bar on top, telling us that we're looking at a vector, a flux vector of heat, is equivalent to minus little k times the gradient of your temperature. And this looks a little bit scary, but don't worry about it. So little k is nothing more than the thermal conductance or conductivity of your material. And so if we're looking at aluminum, for instance, K is a material property that you just look up on Google, and you can find that, K for aluminum is equal to 237 watts per meter squared per Kelvin. And so this is describing how easy it is to push heat through this material. And so, your intuition about metals should tell you that metals are pretty conductive. They're very good heat conductors. So we would expect to find relatively high values of K for metals. And then we're going to note here how this flux is a vector. And we know that temperature is, or we can model it as a function in space. And so if we were living in 3 dimensions, which we are, we know that there's an x, y, and z coordinate. And so the gradient of temperature is equivalent to the partial derivative of your temperature profile in the x direction, partial derivative of temperature in your y direction, and partial derivative of temperature in your z dimension. And of course, you would have I, j, and k hat if you wanted to represent your vector differently. But the point is, taking the gradient of your temperature will actually give you a vector, and that's the reason why you need to consider your heat flux as a vector in this instance. But commonly in introductory college courses and in high school, when you're thinking about heat flux, people are only going to be caring about one dimension because you don't want to have to get too deep into the algebra or the calculus behind all this stuff. So commonly what people do is they'll consider one axis, and we'll just call it the x-axis. And an example problem we can use to kind of lay some more intuition down for this topic is to consider a big, tall aluminum slab. And I'm going to say this is 1 centimeter thick. It's aluminum. And on one side of the aluminum, it's going to be 500 degrees C. On another side of the aluminum, it's going to be 200 degrees C. And the question I have is, what is the heat flux through this material? And in other words, how many joules of energy per second are lost per square meter of this aluminum? And the way we're going to do that is we're going to have to make some assumptions first off. The first assumption we're going to have to say is that we're operating at steady state. And the reason we're going to make this steady state assumption is because we are going to say, we're taking like a snapshot. We're going to say this 500 degrees C and this 200 degrees C are going to remain the same for all time t in order for us to be able to apply these equations that we're about to, because we know in the real world, if we're not operating at a steady state and these temperatures are changing, like if this 500 were to drop down to 300 and this 200 dropped or rose up to like 250 degrees C, well, the problem is that our temperature profile in the x direction will have just gotten less sharp. And because it's less sharp, we now have, and what I'm referring to as less sharp is the slope of this line becomes less and less sharp, and therefore the driving force for your heat transfer becomes less and less. And so you have less and less heat transfer occurring through your medium, in this case the aluminum slab that you're interested in. And so what we have to make the assumption on, and this is something that they like to nail people on at Berkeley with their exams, make your assumptions, state your assumptions. We're going to be operating at a steady state, and in this case we're working with aluminum. I've already defined what our thermal conductivity is for aluminum, and so actually determining what the heat flux is through this material is pretty straightforward. So if we were to just look in our x dimension, we would say that the heat flux in x is equivalent to minus k, and we have this minus sign here because we're referring to heat being lost through our medium. And in addition to that, when you take these gradients, it's in the direction opposite to your unit normal vector. So that's another reason why you have the negative sign, but that's getting a little too deep into the weeds. But the point is, you'll have this negative sign. Intuitively, you can think of it as heat's flowing in the opposite direction, and so you're losing it. We're going to have minus k and then dt dx, and dt dx is describing the slope of this line through your media in the x dimension. And so we can model that pretty simply because we already know these values. So we know that k was equal to minus 237 watts per meter squared per Kelvin. And we know that if I make an assumption that we have a linear temperature profile in our aluminum, I can say that we have 500 minus 200 degrees C, and we're going to be dividing this by dx, and we have to make sure that our units agree. So in this case, we have 1 centimeter, and that is equivalent to 0.01 meters. And another key thing about your thermal conductivity is that the dimensions are actually watts per meter per Kelvin, not watts per meter squared per Kelvin. And I will explain that because we need to make sure that flux on this side will have quantity per area per time, which is joules per area per time. We need to make sure that the dimensions on this side will give us watts per meter per second. I'm sorry, joules per meter per second, which is equivalent to watts per meter squared. And so actually working through this example, plugging in these numbers, you have a calculator, what you find at the end of the day is that we're losing 7,100 kilowatts per square meter of our exposed aluminum that we have. And this is a big deal because we see how important it is to have valid, or how important it is to have insulation in practice, because if you don't insulate your aluminum tubing, for instance, you're losing a lot of heat and you're not able to capture it, so you have to put more heat into your system, pay more money for gas or electricity to heat it back up, and so it's bad. But yeah, that is going to wrap things up for this video. Key thing to remember that I just made the mistake on was thermal conductivity will have units of watts per meter per Kelvin, not watts per meter squared per Kelvin. And that is because when we are evaluating our flux term, we need to make sure that flux will always have units of joules per meter squared per second, which is equivalent to watts per meter squared. And dt dx is going to have units of degrees Celsius per meter. And so K would have to have dimensions to make both sides of these equations agree. And so I am sorry about that, but I do hope that this video was useful for you guys, and thanks for watching.